everyone, welcome to Math Set Go. We are here to make things easier for you when it comes to solving math problems. Learn how to have fun in solving problems and equations, but most importantly, enjoy the process. Are you ready? Math Set Go! For our lesson today, we will be discussing the proof of limit in an indeterminate form. But first, let us familiarize ourselves with the 7 indeterminate forms. Infinity over infinity, 0 over 0, infinity minus infinity, 0 raised to 0, 0 multiplied to infinity, and 1 raised to infinity. Before we proceed to our main topic, let us define what an indeterminate form is. According to Peach's class, an indeterminate form involves two functions whose limit cannot be determined solely from the individual function's limit. These forms are common in calculus. When solving for the limits of these indeterminate forms, we use L'Hopital's rule. Now, let's begin with discussing the proof of limit in an indeterminate form. We will be focusing on the indeterminate form 0 multiplied to infinity. Let us find the answer for this one. The limit of 3 over x squared tangent x as x approaches 0, the first thing we need to do is substitute the approaching value to every x in the function. So this will be 3 over 0 squared tangent 0. Since 0 squared is equivalent to 0 and tangent 0 is also 0, the function will become 3 over 0 tangent 0. Now, 3 over 0 here is equivalent to infinity and tangent 0 is 0. Always remember that if the numerator is not equal to 0 but the denominator is 0, the simplified form of that function is infinity. Therefore, in this limit, the answer is 0 multiplied to infinity. The question is, how can we find the limit of a function if the resulting answer is an indeterminate form? The first step in finding the limit of an indeterminate form is to convert the original function to a simple fraction. To do this, we must first find the LCD or least common denominator of 3 over x squared, multiplied by tangent x. In this case, x squared is the LCD. Since 3 is over x squared and tan x is over an invisible 1, just multiply the numerator and the denominator so it will become 3 tangent x all over x squared. By doing so, we can start applying the L'Hopital's rule to the limit.
Let me give you a brief overview of what L'Hopital's rule is. L'Hopital's rule is a mathematical theorem that allows evaluating limits of indeterminate forms using derivatives. It is an application or repeated application using higher order derivatives of the rule that often converts an indeterminate form to an expression that can be evaluated by substitution. Today, we will teach you how to do the L'Hopital's rule with the example we tackled a while ago. After we convert the original function 3 over x squared tangent x into a simple fraction 3 tangent x over x squared, we are now going to get the derivative of both the numerator and the denominator. As shown, the derivative of 3 tangent x over the derivative of x squared. Let's first start with the denominator. Simply apply the power rule wherein if a variable, let's say x, is raised to a non-zero constant, we bring down the exponent, writing it before the variable, and then subtract 1 from the exponent. In our problem, x is raised to the power of 2. Therefore, we bring down 2, writing it before x, and then let's subtract 1 from our exponent 2. 2 minus 1 will give us 1, and so we are left with 2x raised to 1, or simply 2x. To get the derivative of 3 tangent x, we are going to use the constant multiple rule of differentiation, wherein we can move the constant outside of our derivative operator and then get the derivative of the function of x. In our problem, we can move 3 outside and then we can get the derivative of tangent x. The derivative of the trigonometric function tangent x is equivalent to secant squared x. Now we are left with 3 multiplied to secant squared x over 2x. To simplify 3 secant squared x over 2x, we can apply the trigonometric identity to our numerator. secant squared x in relationship to cosine, it is equivalent to 1 over cosine squared x. Now, we have 3 multiplied to 1 over cosine squared x all over 2x.
Now that we have the derivative of the simple fraction from the original function, we can already substitute the approaching value to this expression. So this will be 3 multiplied by 1 over cosine squared 0 all over 2 multiplied by 0. It can also be expressed as 3 multiplied by 1 over 1 squared all over 0, since cosine squared 0 is 1 squared. Upon simplifying this expression, we will arrive with an answer of 3 multiplied by 1 over 0, or simply 3 over 0. Therefore, since 3 over 0 is an undefined expression, the limit of this function does not exist. We don't need to continue the process of L'Hopital's rule wherein we will use higher order derivatives. That will only happen when the answer that you will come up with is an indeterminate expression. To check our answer, let us graph the function using Desmos. As you can see, it is such a complex graph that both sides approach infinity, which proves that the limit of the function is undefined or does not exist. To further verify, let's check using the table of values. Since 0 is the approaching value, we just have to get one closed value from each side of 0. Here, we chose 0.001 and negative 0.001. It is shown that when we substitute 0.001 to the function, the answer that we will get is 3000.001. On the other hand, when we use negative 0.001, the answer will be negative 3000.001. The values that it approaches are too big, which are approaching infinity. This concept proves that the limit of the function 3 over x squared tangent x as x approaches to 0 is undefined or does not exist. And that concludes our discussion. Thank you for watching this video lesson, guys. We hope you learned effectively with us. Apply all that you've learned from this video lesson and you will surely be able to solve the problems regarding indeterminate forms and L'Hopital's rule. See you at our next lesson, math goers. This Math Set Go episode has come to an end. Math, set, done. Bye, guys!